Hello, this is Guillermo Campitelli, and this is the explainer for the topic linear models estimation. I'm going to use traditional estimation and Bayesian estimation. The topics I'm going to cover in this explainer are first causal models and linear models. So I'm going to explain the differences. Then I'm going to talk about the mean as the simplest of the linear models. The third topic is traditional estimation of the mean. Fourth, Bayesian estimation of the mean. And then I will add one predictor to the linear model and explain it. And the final topic is to do traditional estimation of a coefficient in a linear model. Okay, let's start with causal models and linear models. So causal models, that's the realm of the causality demon. And so remember my particular approach to these the simplest causal model, in which I like to add a constant, so that C, causal variable C, is a constant. So it's not really a variable, because a constant is just one value. So in different participants the value is the same. So it's not strictly a variable, because a variable can take more than one value. And the U is an unknown variable. So we've got the variable of interest, we call it a dependent variable or outcome variable or consequence variable, depending on the context. And the variables that are causing Y, one is an unknown variable or a composite of unknown variables. And the other one is not strictly a variable. So it sounds strange. Well, why do I want to use this model? Because I like to, in this sense, to claim that I'm more Aristotelian than Newtonian. Just in this sense, but not in everything. Because Aristotle, one of the causes of Aristotle is the material cause, or and the other one is formal cause, and this has to do with what something is. And for Newton, cause is what something only applies when something varies, the variation. So in this sense, I want to say, for example, that the height of people, of humans, and depends on differences between people. So difference in genetic components and perhaps differences in nutrition value of different people. But the range of possible height in humans is highly determined by something that we all humans share, which is the 99% of the genome that we have, that we share. So we cannot find a 10 centimeter human, we cannot find a 3 meter human, and that's because there is something that we share that will determine a range of values. So if we don't take that into account, then we don't fully explain height, which is variation. But typically, then, when we go to statistics, we are interested in variation. But that's why I like to emphasize that when we are in the realm of causality, we are not only interested in variation, we are also interested in how things are. But I have to warn, you won't find these in other authors that only use variables as causal variables, not constants. Okay, so if you're uncomfortable with that, this would be the simplest of the models. Some unknown variables predicting the variable of interest, but sometimes that U doesn't appear in models. For simplicity, it is ignored. So this may be the simplest causal model. So we've got a variable Y, and that's it. That's all we have. We don't know what caused that variable. Okay, so let's move to the realm of the probability demon. So the linear model is statistical. So statistics is inverse probability, so to speak, or it shares with probability the use of values, numbers. Is not something that happens in reality. Okay, so we've got two versions of the simplest of the linear models, and the first version is y, which is the variable that we call it outcome variable, or in some contexts dependent variable, equals beta 0 plus epsilon, which usually is considered error or sometimes residual. And then this error epsilon or residual epsilon, we say that it's normally distributed. And remember, in the normal distribution, we need to specify the distribution. We need two parameters, the mean and the standard deviation. And in this case, we fix the mean to 0, and the standard deviation we give the Greek letter sigma, and that basically means that we don't know exactly the value of that distribution. What do? We need that value in order to calculate the probability of finding some error. Well, we are going to estimate that value using the data that we collect in our sample. Now, the second option, which are equivalent. These two options are equivalent. Now, the first one is the most popular. You're going to see in most textbooks. The second one is less popular, but is the one I like the best. Basically, it says that the y variable is randomly distributed, is normally distributed, and now the means are, instead of 0 and gamma, 0 and sigma, is gamma and sigma. Now, for this model, we are going to say that gamma equals beta 0, and sigma, as in the previous version, is estimated using the data we collect in our sample. And again, this beta 0, gamma equals beta 0. Why don't I put beta 0 in the gamma in the first place? Why do I have to do this? It looks like a waste of time and resources. The reason is that in a more complex model that we are going to see later, we are going to change the gamma, and we are going to make it a more complex thing. But by saying gamma equals beta 0 here, the model will have the same structure when it becomes more complex. We just put the gamma there, and we don't have to put the complex mathematical structure in that parenthesis. So a question for you here: why are these two options equivalent? So we went through that in the masterclass. So if you went through the masterclass, you should be able to answer this question. So try to go through the masterclass and see if, with that help, you can answer this question. Why are these options equivalent? Pause the video and come back, that I will give the answer. Okay, so basically, here I have a table with 4 observations. Okay, now the observations are the y variable. The first one is 45, second one 54, third one 53, and then 48. And my model says, the first model says y, so this observation, equals beta 0 plus epsilon. So you can see beta 0 is the same for all participants. That's a constant. When you have the same value for all participants, or units of analysis. Could be humans, could be people, could be animals, and sometimes the unit of analysis could be a school or a city, etc., etc., etc. Typically in psychology, we have humans as unit of analysis. Okay, so 50 is a constant because all the units of analysis share the same value, and then we add epsilon, and epsilon is different. So in this case, 50 plus minus 5 is 45, 50 plus 4 equals 54, 50 plus 3 is 53, 50 plus minus 2 is 48. So now, where this epsilon comes from? It's not in the data. So this we didn't observe. We only observed this, the variable y. So why this? How this is calculated? Well, we say in the model that epsilon comes from a normal distribution with mean of 0 and a standard deviation that we are going to estimate from the data. So the epsilon comes from this distribution that I drew, and that distribution has a mean of 0, and it has a standard deviation of 4. So let's say we start obtaining, let's consider that a distribution, it's a big box with values inside, and we've got millions and millions of values. The value 0 will be the most likely value, but then we've got values above 0 and values below 0, and the standard deviation is 4. That means that between -4 and +4 we will have more than 60% of the values, because it's a normal distribution. Let's say we randomly obtain one value from that. Well, -5, in the first row, it's a likely value in this distribution. Now, -100 would be very unlikely to obtain in that sample, because if we've got the mean is 0 and the standard deviation is 4, and we've got 60%, more than 60% of the values are between -4 and 4, and then we've got more than 95% of the values between -8 and 8, which are 2 standard deviations to the left and 2 standard deviations to the right. Then obtaining a -100 is almost impossible. Okay, so but -5 is very likely. And then in the second case, we obtain a random number from that distribution, and we obtain 4, and then 3, and then -2. And that's the way we come up with this value. Now, the sigma 4 is something estimated from the sample. It's not something that we know in advance. Okay? Now, I was going to say why these two forms of the model, the linear model, are equivalent. Well, instead of putting the distribution in epsilon, I put the distribution, the normal distribution, in y, in the actual variable. Now, so we are saying that y is normally distributed, the mean is gamma, and the standard deviation is sigma. So if it is sigma 4 in this distribution, it will be sigma 4 in that distribution too. Now, the mean of that normal distribution is not 0, it's actually gamma, and gamma, we said, equals beta 0. So gamma is here. So the mean of that distribution equals 50. Okay, so basically what we are saying is that we are obtaining numbers from a box with millions and millions of numbers, and which follow a normal distribution with a mean of 50 in this case. So values close to 50 are very likely or have more probability to be obtained than values further away than 50, from 50. Okay, so we obtain, so the first value we obtain is 45, which is 5 points less than the mean, which is equivalent to an epsilon of -5. The second one is 54, which is 4 points more than the mean. And the third one is 53, 3 points more than the mean. And then 42, which is 2 points less than the mean. And then we obtain the same thing. So the mean model, or the simplest of the linear models, we're going to use it in two ways. One is to predict one individual value of the sample. And then we are going to use this model to make a prediction about the mean of the population. Okay, so here we've got a variable y, which in this case is intelligence, and the gray dots represent the data. So this dot is a value less than 80, this one is almost 80, and this value is 140, and so on and so forth. So the mean of that is around here. Now, so this line indicates the mean, and that is the value that we assume this is the value of the population. So we make that assumption. The mean of the population equals the mean of our sample. And that's the question I have for you. Why do we use the mean of the sample as the mean of the population, or as we assume that the mean of the population is the same as the mean of the sample? Why do we do that? So with the masterclass, I think you can answer this question. Try to revise the masterclass and answer the question and come back to this video. Okay, so the first reason that we have to say is we don't know what's the actual mean of the population. We don't have any idea of what's the mean of the population. We know that we have a sample that we obtain that comes from a population, but we don't know what's the mean of the population. So why do we use the mean of the sample? We use the mean of the sample because we need to use some information that we have available to make that estimation. And the best information available we have is our sample. We don't have anything else. And because that is the case, then we make an estimation based on our sample. That's perfectly okay. Now, why do we use the mean of our sample? Well, the statisticians have worked on this for many decades. And even before computers were invented, and they were doing these simulations sometimes by hand and sometimes trying to make approximations. So basically what you do is you create a population of values, and then you obtain a sample, a random sample from that. And you use some values of that sample to make a prediction of the population. Well, someone might have said, well, let's use the mean of the population. You can use the mean, you can use the standard deviation, the variance, or the range of values, or range wouldn't be okay, but the maximum value, the minimum value, you can choose. And then you say, well, you make a prediction from what population this sample came from. But in that case, you know, because you had the population of values that you knew what's the mean. And then you do that again and again and again. You obtain many samples and you obtain some values from those samples, and you use that as prediction of the population. So what did they find? Well, they found that using the mean, it gives the best estimate of the mean of the population. So that's it. That's why it works, because by trial and error they found that. I'm not showing this, but the best estimate of the standard deviation of a population is the standard deviation of the sample. The difference is that technically the standard deviation of the sample you calculate doing a formula and you divide by n, which is the number of values in your sample. But in order to do an estimation of the population, you divide by n minus 1. Okay, and why do you do that? No other reason than because that gives the best estimate of the standard deviation of the population by doing simulations. Okay, so basically now we use that assumption. So we make the assumption that the mean of our sample is the same as the mean of the population. And then we want to use this model as a predictor model. So basically here we've got a sample represented by these gray dots. But based on this, we want to predict, if we collect more data, what value we are likely to find. And why do we do that? Well, you may want to do that for many reasons, but maybe because we need to decide policies based on what values of something variable we expect, or we have to make a decision based on that. Okay, so it's very useful to have a model that allows us to make predictions. Predictions will have errors, obviously, but we try to make predictions with the least error possible. So the way we do that is we say, okay, we expect values close to the mean of this sample to be more likely. So we expect that if we collect one data point, it will be close to the mean of this sample. It will be 110, 100 and close to between 100 and 120. Further from that, it will be less likely. So that's using the mean model as a predictor model. We are trying to predict the next value, what range of possible values they are probable. Okay, so we are not using the same model, the mean model, but to make an estimation of the mean. This procedure I'm going to explain, I believe it has some use. It's useful. It's not useful, but I think we cannot deceive ourselves and determine that this process is a good process to make an estimation of the mean of the population. And I'm going to explain why. So basically what we do is we assume that the mean of the population is the mean of our sample. Okay, so we use the mean of our sample to make an estimation of the mean of the population. Now, previously we used the mean model using a normal distribution to make a prediction of the next value we can obtain if we collect data. Now we are not doing that. Now we are making a prediction of what's the mean of the population. That's what we want to know. Again, why do we want to do that? Maybe because our policies are important to know the values of populations based on in order to make policies. Or we want to know who is the candidate in an election that is more likely to win. So we make an estimation of a population parameter based on a sample, or a survey that I conduct. So now the process starts by making the assumption that the mean of the population is the same as the mean of the sample. Now, if we start with this assumption, then what prediction are we going to make of the mean of the population? We already assume that is that. Well, so that's why I'm comfortable, and when I studied about how this standard error of the mean is calculated, and I wasn't comfortable with just knowing the formula. I wanted to know, what does it mean? Why do we use that formula? And when I realized what's the process that you have to follow to come up with that formula, I was not comfortable with this process. And that's why I became a Bayesian follower of Bayesian approach, because it follows a different procedure than this one. Okay, so, but we need to learn the procedure, because this has been the most popular procedure for many, many decades, and it's still the most popular. So we cannot ignore it, even though I think it's flawed. And also is flawed, but it has some things that are useful. Okay. Now, what the standard error of the mean, what it does is to, from the assumption that the mean of the population is the same value as the mean of the sample, and we have a population of values, millions of values that follow the normal distribution, with the mean of the population as the mean, with the mean of the mean of the sample as the mean of the population of those values, and the standard deviation is the standard deviation of the sample. So, and then we obtain samples. Let's start with one sample randomly from those values. How many values do I take in the sample? Well, the same number of values that I obtain in my own sample. If I have a sample of 30 participants, then the sampling distribution that we are going to obtain, it has to have the sample that we are going to obtain randomly, it has to have 30 observations, 30 values. And from that, with this sample, we calculate the mean. And we repeat this process thousands of times. So we've got 10,000 samples that we obtain from the population, and we calculated the mean of those samples thousands of times. So now we have thousands of means. And with these thousands of means, we can create a distribution. That's called the sampling distribution of the mean. And what's the mean of that sampling distribution of the mean? Is exactly the same as the mean of the population. Why is that? Well, as I said before, because statisticians try by trial and error. They did actually these things by hand, and then when computers came, they improved by using computers. And when they realized the patterns, and they started to have formulas to avoid having to do the whole thing. So what they found out is that the mean of that distribution is the same. But the standard deviation of that distribution is calculated by sigma divided by the square root of n. So this one. So the standard error of the mean is the standard deviation of this distribution, and is calculated by the standard deviation of the population divided by the square root of n, which is, if our sample was of 30 observations, then n is 30. If our sample is 300 observations, then n is 300. Okay, so then we have a distribution that is much narrower than the one we started with, than the one of the population. So if you see this one, you can see that it's more spread than this distribution. And so I've got a question here for you. Why the standard deviation of this distribution is smaller than that of the previous one? So try to answer by yourself and then come back and I will give the answer. So why is more distributed? Well, imagine that you have to predict one individual value. So one individual value has a huge range of possibilities. But if you have to calculate the mean, to predict the mean of a sample, those means are already summaries that sort of eliminate the more extreme values. So the means are closer to the mean than individual values. And because this distribution is made out of means of samples, then the values of those means are much closer to the mean of the population than individual values. So this distribution is what is called a sampling distribution, because it's a distribution created by obtaining samples. And so the values here are not raw values, the values here are means. So that's why the standard deviation of that distribution is narrower. Okay, let's move to linear models with one predictor variable. Okay, so this is again the realm of the causality demon, but we are going to leave her alone for the time being. And remember that we had this C, this constant that is my idea, this U, which is unobserved variables or unknown variables or unmeasured variables that we don't know, but they are affecting Y. And now we have a variable X that is a causal variable, and we do measure, we know the value. So this is the simplest of the models in which one known variable affects another variable. And this would be, if we consider traditional causal models, this is what you're going to see. X, arrow, Y. And basically, in order for the assignment, this is the type of models we are looking at. You need to forget about the constant and ignore the unknown variables. So in the model, we are going to use this type, or a bit more complex, but we are only going to use the variables that are measured, that we know. Okay, so the linear model now becomes a bit different. So before we have only beta 0, but now have two parameters, beta 0 and beta 1. Beta 0 is still a constant, but now beta 1 is also a constant, but in this part of the equation is going to be different for each value of x. So beta 0, so this part of the equation is beta 0 only, so it's the same for all the participants. But this this part of the equation varies, because beta 1 is the same value for all participants, but x is different. So beta 1 is going to multiply by a different value for when x is different. And this part is the same, plus epsilon is the same, and epsilon distributes normally with mean of 0 and standard deviation sigma. That's the same as before. And equivalently, the y in the second option, y is normally distributed with gamma and sigma. You can see now why I put gamma before, and I took the trouble to put more terms, but it becomes more handy now because I don't have to put the whole beta 0 plus beta 1 times x in here. Just put gamma, and then I define gamma by this formula. And these are equivalent as well. So the explanation is a bit different than the previous one, but the rationale is the same. So if we look at the first formula, y equals beta 0 plus beta 1 times x plus epsilon. So we've got y 40, beta 0 45. Then we've got beta 1 times x. Well, this is 0 because x is 0. And then we add epsilon minus 5. So basically it's 45 minus 5 is 40. Second row, 51.5. Where does this come from? Well, beta 0, 45, plus beta 1 times x, so 0.5 times 5, which is 2.5. And then that's we have to add 2.5 to 45, so that's 47.5. And then we've got to add epsilon, which is 4 in this case, so the sum is 51.5. Okay, so these I use the first two rows to explain the first option of the equation of the linear model with only one predictor variable. And as we did before, the epsilon has a mean of 0 and a standard deviation of 4. Okay, and these are the same values as before. The beta 0 is different than before, because beta 0 now is not a mean anymore. It's what we call the intercept. What's the intercept? Well, that's the value of variable y that is expected if the value of the variable x is 0. So we can see it here in sigma. If x is 0, the expected value is sorry, not sigma. This is gamma, not sigma. So the expected value for 0 is sigma, which is 45, which is the same as beta 0. So this is the intercept, the value for y we expect if x is 0. But of course we have some error. That prediction is not perfect. And in this case, the error was minus 5, and the observed value is 40, not 45. Okay, so second formula. We say that y is normally distributed with values gamma as mean and sigma as standard deviation. And standard deviation should be the same in the two distributions. So let's see how we come up with that. So now we say that gamma equals beta 0 plus beta 1 times x. So gamma is here, and we've got the values calculated from beta 0 plus beta 1 times x. So this is gamma. And now gamma becomes, this is the expected value for each x. So if x is 0, we expect 45. If x is 5, we expect 47.5 in y. If x is 10, we expect 50 in y. And if x is 15, we expect 52.5 in y. So here is y. We didn't observe those values because we don't expect our prediction to be perfect. But those values should be close to our prediction. So you can see that gamma is the mean of that distribution. So the difference with the mean model is that now gamma is not going to be one value like it was in the mean model. Gamma will be different for each value of x. Okay? So basically, what if let's go to the last two, because we used the first two to explain the first equation. So expected value for y in this case is 50, but we are saying that the values of y come from a normal distribution, and the mean of that distribution is gamma, and gamma is 50. But 50 is the most likely value, but it's not going to be exactly 50. So in this case, we've got because it comes from a distribution with a standard deviation of 4, then we obtain for 53. And for an x of 15, now the expected value is different than the expected value for an x of 10. It is 52.5. But again, we don't expect exactly that value. We expect values that are that value or close to that value. And in this case, we obtain 50.5. So the idea is the same as before, but now the prediction for the values of y depend on the values of x. And that's the important thing. That's what we are interested in, the relationship between x and y. Now, before, y didn't depend on any value of x. But in this case, y does depend on values of x. And it will modify its value according to the values of x. Okay, so this is the model using the linear model to make predictions about individual values. So now, before we had the gamma, it was a single value in the mean model. But here, as I just explained, it takes a different value for each value of x. So for 0, x being 0, gamma is here. For x being 25, gamma is there. For x50, gamma is there. For x75, gamma is there. And for x100 is around here. So as you can see, this is the job of choice variable here is not a good predictor of intelligence, because this line varies a little bit, but not much. Okay, so it's different. It's a bit higher in 100 than in 0, but very little, by very little. So in that case, job of choice is not a good predictor of intelligence. We can see that by a visual inspection. We don't need the formulas. Now, as I showed before, we've got a normal distribution. Now, here I present a few number of normal distributions, but in reality, this should be infinite number of normal distributions. Basically, we are saying for value 25 of x, we expect a value of y that is a bit more than 110. A bit more than 110. But values that are probable are within this distribution. Okay. So the last topic is the traditional estimation of a coefficient, but I am mindful that I skipped the Bayesian estimation of the mean, which I'm going to do at the end. Okay, so I'm not going to explain this in detail, just saying that it's the same procedure than in the estimation of beta 0 in the mean model. So beta 0 in that case was estimating the mean. But what it's done in this case is, instead of from the population of values with a mean that is the mean of the sample, now that population of the values, what we know is not the mean. We know that those values have a we've got X values and Y values in that population. And when we calculate the beta 0 and beta 1, those values are the same as the ones we calculated in our sample. We sometimes, here it becomes very sloppy. You're going to see in textbooks and in myself as well, that sometimes the parameter in the sample, we call it B0 and B1 instead of beta 0 and beta 1. But sometimes people become sloppy and they use the same Greek letter beta to refer to the sample as well. It's unfortunate, and I also you blame myself as well, because I do that as well. But basically the idea is that in the population we've got a beta 0 and beta 1 which is similar to the one in our sample. That's the same we did with the mean. We assume that in the population the mean is the same as the one in the sample. And then we obtain random samples of the same size of our sample, and we obtain the beta 0 and beta 1 in each of those samples. So now we've got 10,000 samples, and each of them has a beta 0 and beta 1. So we now have a sampling distribution for the beta 0s and a sampling distribution for the beta 1s. And that is the sampling distribution of these parameters, and those have a standard error. And again, when we ask the question why the standard deviation of this distribution is smaller than that in the previous one, well, which the previous one we are referring to these distributions, well, it's smaller because we are here making predictions about individual values, whereas here we are making a prediction of the parameter of the beta 0 and the beta 1. And I forgot to mention something important. I apologize. So we've got two parameters. Beta 0 is the intercept, which is the value of y we expect for a value of x of 0. And beta 1 is the slope. We call it the slope of this line. So this linear model is called linear model because it is a line. The model is a line. And the slope is the amount of how much y increases as we increase 1 unit or 1 point in the value of x. So here, for 1 unit of increase of x, y increases very little. Okay, but that's beta 1 is the slope of this line. Now, try to answer by yourself what is wrong with the traditional parameter estimation procedure, and come back and try to answer the question. Well, the answer is that to me it's wrong to make an assumption of the parameter of the population, and then we make an estimation of that same parameter. So why do we make an estimation if we already assumed the value of that parameter? So that's flawed to me. Statisticians obviously know this. It's not that they don't know this. But doing something different it was impossible in the past because there was no computational power. The Bayesian method that I'm going to explain now requires a lot of computational power when the model becomes a little bit complex. Not very complex. A little bit complex requires already a lot of computational power. So though the Bayesian models were not popular because we didn't have the capability to make them work. And now that we have, then we should be abandoning these models that are flawed. Now, they are flawed, but they are not completely useless. So when we make an estimation in our 95% confidence interval of the estimation is a large range, that means that our estimation is not very good. If the 95% confidence interval is a small range of values, our prediction is better. And that's absolutely true. So there is a flaw in the procedure, but this aspect is not flawed. Small confidence intervals give us more confidence in that prediction. Larger confidence intervals doesn't give us less confidence on our prediction, and that's it true. And why? How do we get the confidence intervals smaller or larger? We do that by the sample size. Remember that the n we have in the formulas to calculate the standard error, and the larger it is, the n, or the number of observations in our sample, the smaller the standard error. And that is a fact. And so when we have large samples, our predictions will be better. So that's a good aspect of this procedure. It helps us in determining how large our samples should be. But as a procedure to make an estimation of the population, it's flawed. Now, the Bayesian estimation, I believe, is a step forward, an improvement, and that's what I'm going to explain next. Now, for the Bayesian estimation of the mean, I've already explained in the masterclass, and I'm going to just give a very brief new explanation here, a little bit of a different angle. But I wanted to spend most of the time in the traditional methods because we are going to basically abandon them soon, whereas the Bayesian method, we're going to go through it in the next lectures. So this is like a second angle to what we saw in the masterclass, but we are going to go through these issues in further lectures. So this is going to be relatively brief. Okay, so Bayesian estimation or Bayesian statistics are based on the idea of updating knowledge, updating beliefs about things. Okay, so we start in this flowchart, we start with previous knowledge. Previous knowledge means knowledge before collecting data. We make predictions based on that knowledge. And then we acquire new information, which is data in this context. And then we update our previous knowledge to new knowledge. Now, this new knowledge become previous knowledge for data that we're going to collect later, and this flow chart begins again. And we've got a continuous flow chart of previous knowledge, prediction, new information, new knowledge. Now, my question is for you, where is the prior distribution here in this flow chart, and where is the posterior distribution? Pause the video, try to answer the question. Okay, I think this one is quite easy because the wording gives you the idea. Previous knowledge is the prior, so the prior distribution is here. Now, this is the data, and new knowledge is the posterior. So posterior means it's our new belief about parameters of the population based after observing data. Prior distribution is our beliefs about the parameters of the population before observing data. Now, if we are good Bayesians, we are not going to start from scratch every time we run an experiment. We are going to use the previous knowledge in order to inform our prior distribution of the new experiment. Okay, now, let's see the theorem. That's the Bayes theorem, and it has 4 components. This is the prior, probability of theta. That means probability of possible values of the parameter. When the parameter is the mean of the population, well, theta is here a range of possible values. Could be 20, 21, 22, 23, 24, 25, 26. These are possible values of the parameter of the population. So this theta here is a placeholder for possible values. And that's the prior probability, is the belief we have before collecting the data. The posterior is the component that we are interested in. We are interested in what's the probability of what's the probability that the population parameter takes different values, same as with prior. But this bar D indicates that given the data we observed. So D stands for data and theta for parameters in the population. So given the data we observed, now what's our belief, our probability of possible values of the parameter of interest? Okay, so how do we get to here from there? So, but basically this is the movement that we are interested in. We start with a prior, we finish with a posterior. Now, this is what typically called the likelihood. I'm not going to go into details that why I say typically, because it is the likelihood, but I don't like that that term. But it is a bit complicated to say why. I'm not going to go into that. But basically is, what's the probability of the data we observed given different parameter values? Okay? And this is the difference with the procedure or one of the differences with the procedure we did before. In the procedure we did before, we said, okay, in our sample, we obtained the value 25. Now we assume that theta is 25 in the population. And based on that, we determine how likely, how probable was to observe the data we observe. Okay? Now, in the Bayesian approach, we don't make that assumption. That's what I like of this approach. We actually consider each possible parameter value for the mean. If the possible values for the mean are between 0 and 100, we consider all the possible values. And for each possible value of the mean, then we determine what's the probability of obtaining the data we obtained. And we do that with a distribution that it's the same as the one used in the traditional method. Typically, if we are with continuous variables, it's going to be a normal distribution. So the distribution, the sampling distribution is the same, but instead of doing 1, we calculate 1 for each possible parameter value. And then we multiply by the prior, and then that's with just this part, that becomes what we say proportional. The posterior, what we calculate here is proportional to the posterior. Sometimes this probability of the data is very difficult to calculate, and we don't calculate it. We are happy enough with having a value that is proportional to the real posterior. But if we can, in simple context, we can calculate this, or we approximate this. We use tricks for that. Actually, we very skillful mathematicians use tricks, not myself. To use algorithms to calculate these, but conceptually, this is this means that let's say that theta can take 3 values. That's for the sake of argument. It usually can take infinite number of values, but theta could be 1, 2, or 3. So we do this calculation for theta 1, then for theta 2, then for theta 3, and then we add all these values, and this is the probability of the data. So this is the probability of the data given one of the possible values. This is the probability of the data given any possible value, not just one. So that's the theorem, and I'm going to try to explain very briefly with a graph. Now, and before moving on, I'd like to show that these Greek letters are very frightening sometimes. People think there's something mysterious. We use Greek letters, it should be something complex. It's not. The Greek letters we use Greek letters for parameters of a population, and that to distinguish from things on a sample. But they are placeholders. So sometimes I said, well, we can use an emoji instead of a Greek letter, and it would be exactly the same. And when I was looking for emojis, I found the trolley that I used for buying food is a very good metaphor, because you can add different things there. You can add different values. So if this helps you and keeps you allows you to get rid of the fear to these Greek values, then just use that. It's the same. Okay, so now this is something that I'm going to go quite fast. So please don't worry if you don't get it this time. I'm going to explain this in further lectures again. So, but this is what is called the likelihood, and the likelihood is calculated by assuming for each possible parameter value, and here we are saying that possible parameter values are from -500 to 500, so a large number of possible values. What is this? Well, it could be a mean, it could be a difference between means, it could be many things that we are interested about a population parameter. Let's say here it's a mean, and it could be anything in the population between -500 and 500. Now, for each possible value, we use a normal distribution to say what's the most likely value. Now, remember that when I used the traditional method, I showed many normal distributions transposed. And well, here is the same, but because I can't put infinite number of normal distributions here, then the normal distribution, instead of determining the probability using a curve, is determining probability using color. So dark color, it means higher probability. And then it goes to the lighter browns are the brown is a bit less than the black, and then the orange a bit less than the brown, and the white is even less, and blue is almost zero, zero or almost zero. In a normal distribution, you will never have zero, because but it goes from -infinity to positive infinity, so it's not exactly zero, but it could be a very, very, very small number, close to zero. So basically what it's saying here is, if let's say the mean of the population is -500, then what are the possible values of the mean of the sample that we collect? Well, this distribution is giving this information. So -500 is the most likely value, but values in this range are possible, and within beyond that range are impossible or very close to zero. For a negative 100, the most likely value in the population, in the sample, is negative 100. And again, values closer are still probable. The further away you go to negative 100, the less likely. And for, say, 400, the most likely value in the sample is 400, but still values close to 400 are likely. Values that are not close to 400 are less likely or almost impossible. So that's the likelihood. That's the way we come up with the likelihood. Now, we need to determine the actual likelihood, we need the data. So the data, let's say, is 0. If the data is 0, now the likelihood is this. Now, likelihood it's like a probability, but it's not a probability. Why is that? Because these values do not add to 1. Whereas in a probability, values should add to 1. In fact, because it is a normal distribution and continuous variables, they shouldn't add to 1, they should integrate to 1, as I explained before. So, but if we go vertically, those distributions for each parameter value, they do integrate to 1. But these ones horizontally, they don't integrate to 1. That's why they call it likelihood, because if we call it probability, and it should add or integrate to 1. Okay, so if we observe that the data is 0, then this is the likelihood of the data, or likelihood of the parameter values. If the data is 200, then we look at this, and this is the likelihood. Okay, now then we need to add the prior. Okay, so in this case I added a uniform prior. A uniform prior means that, and remember, the prior is the belief I have about the parameter values, possible parameter values, before collecting the data. And in this uniform prior distribution, I'm saying I have no idea. I don't know what are the possible values. What values are more likely than others? I have no idea. The only thing I know is that less than negative 500, the probability is 0. So it cannot possibly be less than negative 500. And more than 500, probability 0. So it's not possible for values to be more than 500. But for values, any value within that interval, the probability is the same. Okay? Okay, now when we multiply this, which is the probabilities we use for the likelihood, by these probabilities of the prior, that's what we have to do in the Bayes theorem. Well, these values relatively are not going to change because we are multiplying by the same value. So it remains the same. Now, in this case, I changed the prior. The prior is still a uniform distribution, but now is restricted the range from negative 250 to positive 250. So what it's saying is that values less than negative 250 and values more than 250 are impossible. Probability 0. So what happens is that when I multiply these prior by the probabilities to generate the likelihood, then these values here become 0 now, because we are multiplying by 0. And values here are also become 0 because we are multiplying by 0. And these values are relatively going up relative to the values that went to 0, obviously, but between themselves they remain the same because they multiply by the same value here. Okay, now in this distribution, that's typically we use a normal distribution, but sometimes the uniform distribution we can use as well. We are saying that values around 0 for the parameters of the population are more likely than values away from 0. So when we multiply this, which is the same, by this distribution, this prior distribution, these values close to 0 go up in value, and the values further away from 0 go down in relative terms. And the values here also go down. So that will change the values here. And we can have a prior that is not a normal distribution. This is a skewed distribution, and basically what it does is we multiply this, which is the same for than the ones we saw before, by this, then these values here go up and the values away from this go down, and values here go down. So we have the prior and we have the likelihood, and we multiply them and we show what's the effect. Now we obtain the data, and the data, we obtain a sample, and the parameter of interest, let's say the mean of this sample, is negative 200. So we go to negative 200 and we've got, we use this row, and that is the likelihood times the prior given the data we observed. And we are this sign means it's proportional to the posterior. It's not equal, because in order to be proportional we have to divide by the sum of all these values, but sometimes it's very difficult to calculate. So let's say we started with this prior and these values for likelihood, that when we observe that the data is negative 200, this becomes the likelihood. So when I multiply these values times these values here, that gives me a new distribution. And the distribution will be similar to this, but more with a peak in 200. So it's much narrower distribution than before, because we before observing the data, because of previous studies, we thought it was around 200, but we gave to values that are away from negative 200 some credence that they are possible. When we observe that in our data is negative 200, now the values that are further away from negative 200 become even less likely than before, and values close to negative 200 become more and more probable. And that is the posterior distribution. And in that new posterior distribution, we can have a confidence interval. Bayesians like to call it the credibility interval to differentiate from the 95% confidence interval. But that credibility interval is an interval in the posterior distribution, which is different than in the traditional method, in which the 95% confidence interval comes from a sampling distribution. Now, what problems do you identify in the Bayesian approach? That's something that I leave it to you as an exploration, but we probably don't have the elements at the moment, but perhaps you can think about it. So Bayesian approach is not perfect. It's conceptually much more interesting to me, but still have some problems of computation, and I will use other lectures to explain.